In this video, we're going to build our own footprints in KiCAD from scratch. I'll show you the full process, how to manually build footprints, how to use the footprint wizard, how to add 3D models, and even how to make good assembly drawings by using additional layers or by using the fabrication layer, which is what I do. So whether you're missing a component from the library or just want to make your own standard library, this is something that will be very valuable to you when you're designing your own PCBs. Footprints in KiCAD are stored as .kicad_mod files, and they live inside a .pretty folder, which is something like this as you see on the screen now. So if I was to take an example of microcontrollers, inside there you can see I've got two footprints as a TQFP64 and LQFP100. And you can see the extension for this is .kicad_mod. So this is KiCAD's way of organizing footprint libraries. It's simple once you see how it works, and we'll create one from scratch today. Before we start, a quick thanks to PCBWay for sponsoring this video. If you're designing your own footprints, you'll probably want to see how they look on a real PCB. PCBWay makes that process ridiculously easy. They offer PCB fabrication, assembly, CNC machining, and 3D printing, all from the same platform. You can upload your Gerbers directly from KiCAD, preview your board online, and they'll usually ship your prototypes within just a few days. I use PCBWay for my own projects because the quality is great, and you can even get different solder mask colors or surface finishes if you're feeling fancy. There's a link in the description below where you can check out the current deals and start your first order. Thanks again to PCBWay for supporting the channel. So let's start with the manual method first. This is how you get full control over everything. I'll create a new footprint using the footprint editor. Let's call it something like my custom SOIC, just as an example. So I'm going to open the footprint editor first, and I will basically create a new footprint. But before we do that, let's create a new library as well. So I have my libraries like this, and this library, I'm going to do a new library, call it a global library. So a project specific library will live within the project that you're creating the library from. And a global library will basically be available for all future projects. So I tend to only create global libraries. Go to the location where you store your libraries. So for me, that's documents, KiCAD, library, and then I have a footprints folder. And in there, I'm just going to write EE test. So I know I need to delete this later on, and press save on that. Once you've created that, if you scroll down, you will see your library somewhere down here. It is organized alphabetically. So if you right click this, then you can pin this library if you want, and then it will always appear at the top. And in there, I want to right click and new footprint. You can also click over here as well. Once you've done that, you will basically end up with something like this. And I'm going to click save as, let's say my custom SOIC. Select the library you want to save it into and press save. So you can see the old one stayed there as well. So I'm just going to delete that. Now for the component name, I would typically give it the name that kind of goes with it. So if it's an SOIC or something like that, then that's the name you want to give it. If it's a very custom kind of symbol, then maybe just give it the part number name. So if you look at some of my components over here, they will have part numbers, and some of them will have SOIC because obviously that's used across multiple components. So I can reuse them for some components, whereas a switch, for example, will have a very specific layout, and for them I tend to just give it a part number that the footprint belongs to. So in this component, what I'm going to do first of all is delete this because I don't like it. I want the reference, and I want this reference as well, which is on the silkscreen layer, and this is on the fabrication layer. So first, I'm just going to place a pad manually on the workspace over here in a random location. And you can see the pad has a pin number, and this will align with the pin number on your schematic symbol. So I'm just going to change that to 1. It typically would start with 1 anyway. In this window, which you get by double clicking, you basically have some properties for the component itself. So now I don't have a reference component, so see if I can find something to use as a reference. So I'm going to use this ST microcontroller as an example for creating this SOIC chip. Typically in a datasheet, you will have a recommended footprint for the component. Now, most of the time you will have a similar footprint available over here. Sometimes you will not. And at those times you'll have to basically create your component manually, which is what we're doing at the moment. So let's look at this basic symbol over here, which is SOAN package. And you can see it gives you a bunch of information, including the pitch, which is the space between your pins. It gives you the size of the pad, and most of the time it won't give you all the information, so you'll have to do some calculations. So for example, in this, it doesn't give you the width or the height, depending on how you want to look at it, of this pad. So what you have to do is 6.7 minus 3.9 divide by 2 to get this pad size. So let's put that in over here, and this is the pad that I'm creating. So for the width, I've calculated it as 1.4, and you got 0.6 as the this dimension and 1.4 for this dimension. So double click on the pad itself. I want X to be 1.4 and I want Y to be 0.6. Press OK, and then we'll need to change the location. So you can see the Y location is already at 0 and the X location is at minus 4.51. So from here, we'll need to calculate what the X location needs to be. And you can see that information is not given to us, so we'll need to work it out. So that information is basically 3.9 plus the size of this width over here, which is 1.4. So what you can do in here is just type in 3.9 plus 1.4 and you get that information basically. So that's minus 2.5. So what I'm going to do now is basically place a new pad which will have the same dimensions that we need, and we can basically modify it to suit what we want from our component. So if you go back to the drawing, so obviously all of these pads are in a line, all of these pads are in a line, and they're going to be aligned this way as well. So we want to make sure we're following that. And the pitch is 1.27. So 1.27 on the Y and 2.5 over here. So let's keep placing our pads. Another thing we might be able to do is actually use the grid to help us. So if let's try it out, maybe not in this case as it doesn't seem to be working. You can also put maths in here. So 1.27 times 2 and 1.27 times 3. Now the other side is just going to be a reflection. So now that we have our component, what we can do is put down a silk screen and a basically an outline if you need to. So we know the size of our component from over here, and pin 1 is on this side. So our silk screen typically would look something like this. So you do the outline of the component 2-dimension, and then in KiCAD there is typically a triangle that's used. So if you want to continue following that, you can do so. The triangle looks a little bit better than this generally. So for pin 1, there might be a triangle, or you can basically denote it in another way. So you can do this as well. There are multiple ways of showing pin 1. So you can do a circle inside your component. Now what I like to do is move this to the middle and basically reference to the top over here. Obviously delete one of them that you don't want. Now this is just a quick way of doing a component. So obviously I've not measured the dimensions or anything like that. And then finally you want to do your courtyard, which is basically your clearance around the component. So you don't want any other components to be within a certain area of this component. Now if you look at some existing components that are like this, we'll see something very similar. So let's look at a SOIC 8. You can see there's a courtyard around the component. You can see there's a silk screen. You can see there's a pin 1 indicator, and then there's a layer on the fabrication, which I'm going to get to now. So if I go back to here, you see we have this reference, which is on the fabrication layer. Now you can use the fabrication layer, or you can use one of the other layers if you want as well. And this basically helps you create a assembly drawing. So for this component, you can basically draw a square like this, and on the component below, you can see that the component actually looks something like this. So there's a line over here, there's pin 1 and pin 8. So you can make the fabrication layer look like your component if you want, or you can have it similar to your silk screen and just show the pin 1 indication and the size of the component. Now what this does is lets you print a assembly drawing very easily. So when you are doing your outputs for PCBWay, you can just basically go to print, and you would print the edge layer and the fabrication layer, and it would give you your reference designator with this, and it would give you this outline over here as well for your component, and you'd get a very neat looking assembly drawing for your PCB showing where the component location is. Now generally this grid will help you. If you're doing a component that's on a 2.54 grid, you want to use the grid to help you put down your pads. So I used the 1.27 and that did help me out. obviously might not always help you out in this direction, but most of the time the grid will help you out put down your pads properly. But you can also check the placement of the pads by looking at the numbers as well. So after the pads, obviously we added the outline, the courtyard, which is the pink line over here, which defines the physical space the component needs for clearance. The silk screen will obviously show up on the board itself, and the fabrication layer is for assembly and documentation. So it basically shows the component body accurately and shows pin 1. And another thing on the fabrication layer is the reference. So your PCB may not have space for the silk screen, but you can always show the reference on your assembly drawing. Now, if you don't want to use the fabrication layer, you can use other layers as well. So typically someone might want to use fabrication layer for like a panel drawing or something like that. So if you don't want to use the fabrication layer, do your drawings on the other layers. You can have this reference on multiple layers if you want as well. Now let's take a closer look at the pad properties. So I double click on one of the pads over here. We already had a look at the dimensions, which we put in from our reference. We looked at the position as well. Now pads can be SMD, which is what we have in this case over here. They can be through hole, they can be an edge connector, or they can be a non-plated through hole, which if you look at some of your USB-C connectors, they'll typically have 2 non-plated through holes on there, or they can be SMD apertures. Now, each of this type obviously affects what the footprint looks like. So if I was to put down another pad over here, for example, and let's say we call this pad through hole, you're going to get more settings over here. And you can see we have a through hole over here. Let's put down another pad. Let's call this non-plated mechanical with a 1mm diameter, and typically you want to have that as circular as well, and the diameter of that as 1mm. So now if you go to the 3D viewer, you can see this over here is our silk screen. So you got non-plated through holes, you got a plated through hole over here, and you got the SMD pads as well. Now I've used obviously through hole, SMD pads, non-plated through holes. I don't typically use the other ones. The SMD aperture is basically for your stencil. So if you wanted to have a cutout on a stencil, you can put down a pad, and this will basically create an aperture in your stencil so that solder paste goes through. And you might want that for whatever reason. Now in here, you also have connections. So connection basically tells your PCB design if you should add a teardrop here and what the teardrop should look like. Now teardrops typically reduce stress on tracks. So if you didn't have a teardrop, obviously your track would end over here. And if it's high vibration environment, then there's a chance of cracking, and this reduces that chance. I'm not going to worry about this too much for this design. Obviously you're stepping into more advanced topics there. And then you have pad clearance, and this is basically clearance around your component and your solder mask and your solder paste clearances. Now typically you don't need to mess around with these values, as the manufacturers will deal with it. So if you just leave it as it is, you should be fine. But if you wanted to, you can expand your solder mask around your component. So you can see the solder mask is going outside of your component, and this might be for very small pads, for example. Now typically you don't need to mess around with this value, as your manufacturer will deal with it. If you're using fine pitch components or something like that, then you might want to set this manually by yourself. It basically controls the clearances of certain layers around your copper pad. If you increase this too much, there's a chance that this clearance touches the next pad, and it's a lot easier to get solder bridging and things like that. So solder place clearance, obviously I think you can have negatives in here as well. Controls how much clearance you have for the stencil. Now if you make it too wide, obviously then you're going to overcover the component. So if you make it smaller, you're going to use less solder paste on the board, and that could mean that you don't get as good connection. Typically if you increase the clearance, then you're going to get more solder on that pad. So I think typically just leave it as is. You don't need to worry about these settings for most things. Now your component will have certain layers ticked by default, and they will change, I think, depending on what you select. So if you selected a through hole, then you just get the mask. If you selected an SMD component, you get paste and mask. So you want to leave them as is. If you do need adhesive on your components, then you'll want to select that as well. Now let's try to create this component using the footprint wizard. So what I'm going to do, I've saved this component. I'm going to go File, Create Footprint. And what I want is SOIC. So I'm just going to select SOIC from here, press OK. And then I'm going to say pads, I have 8, rows, I have 2. The pitch is 1.27, the pad width is 0.6, and the pad length is 1.4. And the row spacing, I think we calculated on the other board, was 3.9 plus 1.4, 5.3. So I'm just going to type that in as well, 5.3. I'm going to change the silk screen to be inside the component because that's what I prefer. And then I'm just going to click Export Footprint to Editor. So now we've got our component. The only thing we don't have over here is the reference that we had on the other one, which is basically typed in reference like this. So make sure you add that in, and then you can add in your fabrication layer as well. And easy as that, we've created a footprint using the footprint wizard. So this way you don't have to manually place every pad. This only works for easy components. So in Footprint Wizard, you can see, not everything is available. So I'm just going to go in Test and save this as SOIC8. So obviously in Footprint Wizard, you don't have everything available, but quite a few things are available. So QFET, QFN, QFP, BGAs, things like that. And this is for odd size components. So if you have a SOIC with 10 pins, for example, that might not be available as a standard package in the default or in the KiCAD default libraries. What I would typically do is find a similar package. So for example, this one, which has a similar pitch, similar size, and I would basically open that, click Save As, and save it into my own library and then modify it to suit my needs. I found that to be the easiest, and I typically delete this because I don't want this on the fabrication layer. It adds a lot of clutter. So we created a SOIC package using the footprint wizard. You just enter in the number of pins, the pitch, pad shape, dimensions, and KiCAD will generate the footprint automatically. It's parametric, so you can quickly make variations of a similar component without rebuilding them from scratch. Think under the hood, these wizards are written in Python. And if you're a more advanced user, you can script your own to make repetitive work instant, like creating a full range of connectors in one go, if that's your sort of thing. Now let's do one more thing to our component. So we created this component, obviously, and in the 3D viewer, it looks like this. You can add a 3D model to this. So if you go into the properties window, so footprint properties over here, 3D model, click the plus button and then navigate to your 3D models. Now I think I have a SO8 package. So I'm just going to select that, and you can see this one is not quite right. So you can rotate it, and you can see that was a perfect footprint that we've created, and it matches up with the 3D model that we have for this component. Now 3D models aren't always available, but manufacturers are getting better with this sort of thing. So if you ever build a footprint of your own, I would say always try to get a 3D model, and it basically helps you error check. So you can see my silk screen is a little bit large on this. It could be a bit smaller if you wanted to, and you can check that all the pads line up, and in this case I think they line up perfectly, so we're good on that front. Now if I go to 3D viewer again, you can see the footprint will show up with the 3D model in place, and when you use this footprint in your PCB design, this model will show up there as well. The only thing I would say for 3D models is you add a directory for the 3D models itself, just because if you ever reinstall KiCAD on a different file on a different computer, then those links will break. So if you go my 3D models, and then in there navigate to where you store your 3D models. So in my case it's over here, press OK, and then if you go back to the footprint wizard, it will say my 3D models over here, which next time if you're installing it on a new system, you basically want to get that right, and then it'll automatically find the footprints for you and the models for you. So if your model doesn't line up properly, obviously you've made an error somewhere in the calculations for your pitch or whatever, and then you can change your positions to get it to match up. It might be that the 3D model is wrong, whatever the case, it helps you error check. Once everything is aligned, you can open the 3D viewer and you can see your footprint and your PCB match up perfectly. Now, before we finish, we'll check the footprint for mistakes. Use the footprint checker tool. It'll warn you about unconnected pads, overlapping features, or missing courtyards. So if you run the check and you've got no errors, no warnings, save the footprint in your own custom library. If you don't already have one, just create a new one like I did, and KiCAD will treat it like any other library. Now, if you're working in a team, you can keep your libraries under version control, and I typically have them on a Git repo. So it's a perfect way of controlling things. That way, everyone uses the same verified footprints. Now, I don't tend to have any data on my footprints. So if you go to over here, you can add in fields for parameters for footprints, and I will never add anything like that. And the reason for that is because most of my information is contained on my symbols. So for example, if I show you one of my symbols, you can see all of the information that I need for this component is contained over here. So that includes the manufacturer part number, description, supplier part number, package, all of that's contained here. And this just links to the footprint. And the footprint doesn't have any information because I generate my bill of materials from my schematic and not from my PCB. Now, when you're creating footprints, there are a few things you can read up on, but I won't be covering them in detail in this video. The first one is IPC compliance. So footprints will typically have a standard that they need to meet. So always check your pad sizes and spacings against the components datasheet or IPC recommendations. Your courtyard clearance, obviously when we created the footprint over here, we just randomly created a courtyard around it. Make sure you get the courtyard right so there's no interference when the board is being assembled. Now typically 0.25 spacing from the component body to the courtyard, but this can vary and it will depend on your assembly as well. The footprint editor also has a measure tool you can use. So if I go back to it, you can measure things up if you want to. And you have this one as well, which aligns. So 1.27. And then we can verify some of our dimensions so that we got 5.3 there, 3.9. And I think we had this dimension on our data sheet. So if you go back to the data sheet, you can see 3.9 and 6.7. So both of those match up. So it's one way of verifying your footprint. Obviously, you don't want to carry that forward into your design. And that's the full process of creating custom footprints in KiCAD. So we used the footprint wizard. We also created things manually. We added 3D models. We basically spoke about most of the features that are available. So if you found this useful, check out my other KiCAD tutorials. We'll be moving into more advanced topic next week, and it's basically library management using a SQL database. So it's quite important if you want to do it that way. If you're doing simple projects, I don't think you need to. Thanks for watching and see you in the next one.